Hello all. In this lesson we're going to be studying light. There's a lot to talk about in this lesson, including the speed of light, ray diagrams, Snell's law. We'll even pull out the electromagnetic spectrum. Our bookwork is relatively modest, maybe 55 questions or so. And our aim, which I need you to copy down, is how does light behave and what is the electromagnetic spectrum? And just follow that up with these do now questions. Please do copy them down before class and don't answer them yet. So light moves really, really, really fast, and it moves so fast that we did not know really very accurately how fast it moved until about 100 years ago. It was just simply too fast to measure. However, we do know now that its speed is basically 3.0 times 10 to the 8th meters per second. It's really, really, really fast. It's actually the fastest thing that we know of in the universe. And if you're looking for an equation to do speed of light, you can use this smelly old equation that we've used a lot before. It says v is f lambda, and we can adapt it to say c is f lambda. So you can tell right away that instead of v, we're just using a c. C means speed of light. So the speed of light is the frequency of the light multiplied by its wavelength. Pretty standard, straightforward stuff. Let's do this example question. Calculate the wavelength of a light wave in a vacuum having a frequency of 5.3 by 10 to the 14th hertz, but then express the wavelength in nanometers. So remember, when we use v equals f lambda, we'll get a wavelength in meters, but we'll need to express that in nanometers, so make sure we do that conversion. So v equals f lambda, and in this case, it's really going to be c equals f lambda. C is 3 by 10 to the 8th, which we know, and we also know the frequency. It's 5.3 by 10 to the 14th, so let's rearrange for lambda. Lambda is c over f, and the speed of light is 3 by 10 to the 8th, and the frequency is 5.3 by 10 to the 14th. So let's do this one piece at a time. We'll just do, at first, the 3 divided by the 5.3. And I'm getting 0.566 times 10 to the something, and that something is really going to be the 8 minus a 14, so that's negative 6. But this isn't proper scientific notation. We'll need to move this decimal to the right, which is going to adjust our answer a little bit to be 5.66 by 10 to the negative 7 meters. Now remember, we do need to convert this into nanometers. So the way I like to do these is just multiply them by a conversion factor, where you have meters on the bottom and nanometers on the top. Now we just need our reference table for the rest. Alright, so right here we can see that nano really means 10 to the negative 9. So in other words, that means that 1 nanometer is equal to 10 to the negative 9 meters. So let's get rid of this, and we'll plug that in as our conversion factor. So 1 nanometer is 10 to the negative 9 meters, just from the reference table. So what we really need to do here is do negative 7 minus negative 9. So that's like negative 7 plus 9, which is 10 to the 2. So my final answer would be 5.66 by 10 to the 2 nanometers, which is also 566 nanometers. Alright, ray diagrams. The ray diagrams involve 3 important things. One of them is an incident ray. That is the first ray before it strikes a barrier. So here's an incident ray. It's on its way to hit a barrier. And the next thing you're going to need is a reflected ray. A reflected ray is the ray after it strikes the barrier, and it adopts the same angle in reverse, just falls off the barrier. That's called the reflected ray. And additionally, we have something called a refracted ray, which we'll get to at the end of this lesson. And a refracted ray is one sort of like when the incident hits a barrier and it's transmitted through the barrier, but at a different angle. So refraction has to do with the bending of the light. There is one more thing that we need to know here, which is the normal. It's not completely different than what we've used this term for in the past, but the normal is always perpendicular to the barrier, and it's what we use to define the angles of these ray strikes. So basically, if this angle is, let's say, maybe 45 degrees, then the angle of this ray is also 45 degrees, but you have to compare it to the normal in both cases. Same thing for the refracted ray, it'll also be compared to the normal. Alright, so reflection of light is first. We have this really beautiful, simple equation, which just says that the incident angle is equal to the reflected angle. So it's right here. We have an incident ray coming in, we have the normal at a perpendicular, and the reflected ray is going to look almost identical to the incident. It's just going to be on the other side of the normal, and the angle will be the same, the measure of the angle. I do have one bit of warning for everyone, which is that lots and lots and lots of folks really want to measure the angle of this ray against the barrier itself. So that's a no-no. We do not measure this angle. Instead, we look at the barrier, we draw a normal, and then we measure it against the normal. So that's the convention. I'll write it in here, but do not use this angle between the barrier and the ray to do any measurements. So this is sort of a brain teaser, but let's say that you have an incident ray on a mirror, and it strikes the mirror perpendicular to the surface. So essentially, if the incident ray comes down the normal, what would be the angle of reflection? So of course the answer would be 0 degrees, because the incident angle when measured against the normal, if it's on the normal, that angle would be 0, and the reflection is going to be the same angle, so 0 degrees. So refraction, I mentioned, is when light bends because it's passing through this barrier between two media. Like for instance, when light passes through water and then through glass, or let's say it's going through air and then water, or air and then glass, the light does travel differently in one medium than it does in the other. So oftentimes when it strikes that medium and it passes through, it doesn't pass through unchanged. The light is changed as a result of passing through the barrier. And the typical changes are that the light speed changes, but also its angle of motion also changes. So we call this process or this concept refraction. And we will look at angles of refraction, and we'll even be able to predict those using a relatively simple equation. So let's say that you have an angle of incidence of 0 degrees, like this one. So you have a light source coming down here, and here's the barrier between air and water. So the ray comes down and it strikes the barrier. It's actually not going to be bent at all in this case. It'll go straight through with a refracted angle, which is 0. It won't be refracted at all, really. However, when it passes through this barrier from air to water, water will change the speed of the light. So it'll actually slow down when it gets to water because water is more optically dense than air is, but it won't change its direction. So I just went ahead and added that note in, but let's take a look at this equation, v equals f lambda. V is the velocity of the light, which we just said will decrease. So I will put a little decrease arrow there. And the frequency of the light corresponds to the color of the light. And one of the things you probably have some experience with is looking at objects when they're underwater. I'm sure you've done that before. And their colors don't change, so the frequency doesn't change at all. I'll just put a flat line for frequency. So that means that the wavelength of the light must be decreasing without changing the frequency. And that is in fact true. If the light goes from, let's say, air to water and the speed decreases, then the wavelength will also decrease. The frequency does not change as the frequency corresponds to color. I wanted to point out on this slide before we move on that right here on these spherical glass lenses, you will see actually no refraction at this point on the sphere, and the reason for that is because this is the portion of the sphere where the angle of incident of light is 0 degrees compared to the normal. So it's basically, here's the glass sphere, the light's coming straight down, just like this. All right, let's also talk about oblique angles of incidence, that is, angles that are not zero. So while this is really one process, I will split it into two ideas to begin this conversation. But let's say that we're passing from a less dense medium, such as air, to a more dense medium, such as water. In that case, when you go from a less dense to a more dense medium, the angle of incidence is going to be measured against the normal, just like in the reflection scenario. And then when it passes through the barrier, you will have a change in the angle of the ray. Now, in every case, when you go from a less dense medium to a more dense medium, the ray will always be refracted towards the normal. So what does that mean? That just means that if this angle is, let's see, 10, 20, 30 degrees, that the refracted ray will also be measured against the normal, but it'll be 10, 21, 22 degrees. And the explanation for that is that it has been refracted towards the normal as a result of entering a more optically dense medium. Now, the other scenario would be what happens if we go from a more dense medium, water, and we pass through a barrier and into a less dense medium, air. The text here says that in this case, the ray will be refracted away from the normal. So you can see that here. If the incident angle, which I'm tracing there, is like 10, 20, 30 degrees again, then the refracted angle would have to be away from the normal or more than 30, and you can see that that's true here. So it's right at about 40, let's say 2 degrees, and that means that the refracted ray has gone away from the normal when it went from a less dense to a more dense medium. I like to tie things into real life when I can. Here's an interesting one. So if you are on Earth, right here, this is you, this tiny dot, and you are looking up over the horizon, then you're really looking in this direction. Sorry. So this is the horizon, it's tangent to the surface at that point. And if you see the sun as if it were up here, that means it's really down here. Here's why. So this is your horizon. The sun is obviously below the horizon, you can see in the diagram. But its rays are going to pass up through the atmosphere at this point, and because it's going from a less dense medium, space, to a more dense medium, the atmosphere, then it's going to bend towards the normal. So here it is bending towards the normal, and it keeps bending all the way until it gets to your eye. Now, when it does get to your eye, your brain is going to assume that it's moving in a straight line based on the way it was moving when it got to you. And when it got to you, it was moving at this angle. So your brain is going to assume that it's somewhere over here. But in reality, it's way down here below the horizon. So there's all kinds of craziness there. But the sun is not where you think it is unless it's directly overhead. The other one is similar, which is when you see something underwater. So this is a more dense medium, less dense medium. So as it goes to the less dense medium, it'll bend away from the normal. So here's the light. It's coming in coming out of the water at this angle, but it bends away from the normal, so it really enters your eye at a slightly different angle. And when that happens, your brain assumes it was moving in a straight line and had not been bent, so it assumes it's down here. So that's why you see the straw as being there, even though it's really way down there. All right, let's talk about the absolute index of refraction. The symbol that represents it is n, n for index, I suppose. And the way you calculate it is you take the speed of light in a vacuum, c, always 3 by 10 to the 8th. And you make a ratio out of it and the speed of the light in that particular material. Now, if you're in a vacuum, it would still be 3 by 10 to the 8th, but if you're in water, it's going to be considerably less than that. If you're in diamond, it's going to be considerably less than that. So we don't really know the speed until we measure it in that substance. But you make a ratio out of those two, and that's how you get the index of refraction. The reference table provides you with a small sampling of those. I believe they'll be in the section on waves. So furthermore on this slide we have this system of equations which relates the index of refraction in one substance to that of another, but it also will relate it to the velocities and their wavelengths. Of note, however, is that if this is the substance number 2, that the velocity for that substance would be inverse to it. And substance 1 also would be like that. But when you go from velocity to wavelength, it's straight across. So substance 1, substance 1, substance 2, substance 2. That may be confusing, so let's put all this to use. The frequency of a ray of light is 5.09 by 10 to the 14th hertz. What's the ratio of the speed of this ray in diamond to its speed in zircon? So this is the portion of the reference table that you need, the indices of refraction. And this 5.09 by 10 to the 14th hertz just means that you're allowed to use this reference table. Now we need to do the ratio of the speed of this ray in diamond to its speed in zircon, just a ratio. So let's do the equation that relates their indices, the n2 over n1, to their speeds, v1 over v2. So they're asking me to do diamond to zircon, so I'll say zircon is number 2. And zircon's index of refraction is 1.92. So I'll write that in as my n2. And n1 will be the index for diamond, and I see diamond's index is 2.42, so that will be my n1. That's going to be equal to v1 over v2. I don't know either one of those things, however, this is going to become our ratio. So let's do, it could either, I mean, your answer could be this, it could be 1.92 over 2.42, or you could punch it into your calculator and see what fraction will come out. So when I did that, I got 0.793, which would be, of course, 0.793 to 1. So that, I guess that's my final answer, but I don't know, I sort of like this one as well. So they didn't really say what it had to be looking like, so I'll go with either one. So Snell's law is pretty much my favorite physics equation. It basically just says that if you take the index of refraction for substance 1 and multiply it by sine of its incident angle, that it'll be equal to the index of refraction for substance 2 multiplied by sine and its refracted angle. So this is the incident angle and this is the refracted angle, index for substance 2, index for substance 1. So with just a smidgen of algebra, if you rearrange this equation, you could make it look like this, where it says sine theta 1 over sine theta 2. It would be equal to n2 over n1, index 2 over index 1. And this has like an official name. That is called the absolute index of refraction. The relative index of refraction, right here. And this is very rarely asked about, but it's also not on your reference table. So just so you know, if you're asked for the relative index of refraction, do n2 over n1. Let's do an example. We have a ray of light in air. It's incident on a block of lucite at an angle of 60 from the normal. To what whole number angle is the angle of refraction? So we are going to use Snell's law and our absolute indices of refraction because we do need the index for lucite and for air, both of which were officially mentioned in the question. There's air and there's lucite. So here's Snell's law, and we are asked to find the angle of refraction of the ray in lucite. So that is going to be theta 2. So eventually we need to end up with theta 2 as our answer. And the best I can do in terms of rearrangement right now is just to say that sine of theta 2 will be equal to n1 sine theta 1 over n2, and then I'll have to do an inverse sine function to isolate the theta 2. So the index of refraction in air is 1.00, and the angle of incidence was 60, so I put in sine of 60, and we need to finish up with the index of refraction for lucite, which is 1.50 according to our table. So when you do that calculation, I can find that sine of theta 2 is 0.577, but I need to do an inverse sine to get the final answer. And after doing that, I can find that theta 2 is closest to 35 degrees. All right, this sample problem, I actually think that it would be best if we do this one in class because we need a protractor and all kinds of crazy stuff. So bring your protractors for this lesson and your straight edges, and we'll do this one in class. So the electromagnetic spectrum is on this slide, and it's also in your reference table. So while the electromagnetic spectrum covers many different kinds of waves, including gamma rays, X-rays, ultraviolet, infrared, microwaves, TV, AM, FM, radio waves, and long radio waves, it also includes visible light. But all of the visible light, all of the light that you can see with your eyes, exists in this very tiny band of the electromagnetic spectrum. Most of the spectrum lies to the right and left of this very narrow band. We do expand the bands down here to show the exact frequencies of violet, blue, green, yellow, orange, and red lights. But just know that there are a wide range of frequencies and wavelengths for electromagnetic rays, and visible light is a very, very tiny part of that spectrum. You should know the following things. Microwaves are used for communications and also cooking, of course. Infrared waves typically carry heat, like when you are laying in the sun and you get that sun on your skin and you feel that heat. That's really infrared waves. Then we've got visible light, clocking in at a whopping 1% of the spectrum. We have ultraviolet light. It's what causes sunburns. It's what is being blocked by the ozone layer. X-rays are, of course, for imaging, but we use them for other stuff as well, including ionizing atoms for ionization studies. And then gamma rays are really cool. They are among the highest energy of all of the electromagnetic waves, and they're emitted by radioactive nuclei when they're decaying, and they're definitely super harmful to cells and tissues. Here's our pair up in summary. I will copy this for you folks. You'll need this slide as well. And thank you for watching.